My last video explained where this formula came from. Remember, this is how we are going to find the area bounded by a polar curve. It's similar, but fairly different to using rectangular functions. Remember, we've got that extra 1/2 out front, and we also have the function is being squared. These are both important differences. And we're going to find that another difference is that it can be kind of challenging to figure out what alpha and beta are going to be. It's generally very straightforward in rectangular world what the bounds of integration are. But if we're not careful, we're going to mess that up in polar world sometimes. So let's start with an easy one, the circle. Okay, we already know what the answer to this is because we already know the area formula for a circle. This is a circle whose radius is 2. So we already know that pi r squared is pi times 2 squared, which is 4 pi. So that's a nice thing to know in advance so that when we try out this new formula, we're going to know whether we did it correctly or not. So the area is going to equal 1/2 the integral of our function squared d theta. Our function is 4 sine of theta. Don't forget to square this, right? We didn't have to square it in rectangular world, but now we do. Now, if you're not careful, you're going to say, oh, well, we're going around a circle, so that means we go from theta equals 0 to theta equals 2 pi. That's all the way around the circle, but that's all the way around the circle that's centered at the pole. Remember that we're starting with theta equals 0, right? Theta equals 0 is, in fact, a tangent line in this case. And then theta gets bigger. Theta goes to pi over 4, and theta goes to pi over 2, and theta goes to 3 pi over 4, and then theta goes to pi. And in fact, as soon as we get to theta equals pi, then we've completed the cycle, and if we go from pi to 2 pi, we're going to just trace out that same circle again. So we don't want to go from 0 to 2 pi, because that's going to trace the circle twice. We're going to go from 0 to 1 pi. Okay, so be very careful with your bounds, especially when we have these graphs that get traced out twice. All right, so anyway, this is something that I think we can handle. We've got 1/2 times 4 squared is 8. The integral from 0 to pi of sine squared of theta, d theta. And if you recall, the way we can deal with the integral of sine squared of theta is with the power reducing identity. Power reducing identity says that we're going to do the fraction 1 minus the cosine of 2 theta all over 2, right? So that's going to allow us to factor out a 1/2, and now we're going to get 4 times the integral from 0 to pi of 1 minus cosine of 2 theta, d theta. All right, so that's something we can integrate. Very straightforward, right? We just get theta for the 1 and minus, let's see, well, cosine integrates to sine. The argument doesn't change, but we don't forget to unchain rule it. And we'll evaluate that at pi and at 0. So we've got 4 times theta minus 1/2 sine of 2 theta is pi minus 1/2 sine of 2 pi. And then when we evaluate that at 0, we get 0 minus 1/2 sine of 0. Well, sine of 2 pi is 0. Sine of 0 is 0. So we've got pi minus 0 minus 0 minus 0. So that's going to be 4 times pi. That's exactly what we expected to get. So it's nice when that works out. All right, so that's the area of the circle using this new formula, 1/2 the integral from alpha to beta of r squared d theta. All right, so let's try another one. This is the same circle, just centered somewhere else, right? So again, we're going to get an answer of 4 pi. This time, we're going to say, okay, well, the area equals 1/2 times the integral of our function squared d theta. This time, our function is just 2. This time, theta goes from 0 to pi over 2 to pi. That's only half of the circle. So then we go to 3 pi over 2 and all the way to 2 pi. So remember that this circle is traced out in a different sort of way than the previous one. So it is definitely appropriate to go from 0 to 2 pi for this graph. Anyway, this is going to be 4 that we can factor out, and that's going to be 1/2 of 4 is 2. So we're going to integrate 0 to 2 pi of d theta. Well, the antiderivative of 1 is just the variable, and that's theta in this case. Evaluate that at 2 pi and at 0. Well, would you look at that? We've got 2 pi for the first theta value and 0 for the second theta value. And lo and behold, we get 4 pi yet again. All right, so different equation, because different, different equation, right? 4 sine theta is a different equation than r equals 2. So, but we end up with the same result, and that should not be surprising since they're both circles of radius 2. All right, back to our original problem, find the area bounded by the spiral, right? And this is that spiral that we were using, the not rectangular area method, but I guess the sector area method to approximate it. We never actually found that value, but we kind of used it to visualize all the sectors. So we're going to integrate this. We're going to put the 1/2 out front. I almost forgot that. It's very easy to forget that, isn't it? We're going to take our function. We're going to square it with respect to theta. This time we're told, we already talked about at least, that theta starts at 0 and theta goes to pi over 2. And then theta finishes off at pi. So we're going to go from 0 to pi. And our given function is 4 theta over pi. Now, don't forget what constants and variables are, right? So we can square all of these, but the 4 and the pi are both constants, so those can get factored out. So 4 squared is 16. 16 over 2 is 8. And then the pi squared can go on the bottom. And then we're going to integrate from 0 to pi of theta squared, d theta. All right, cool. That looks like a power rule sort of problem, which is a little odd. Normally we don't see power rule. We normally are messing with sines and cosines here. But this is definitely power rule. We're going to take the antiderivative of theta squared and get 1/3 theta cubed. And we're going to evaluate that at pi and at 0. So our constants are 8 over 3 pi squared. We'll evaluate theta cubed at pi and at 0. Okay, so we have 8 pi cubed on the top. We've got 3 pi squared on the bottom. That's going to reduce down to 8 pi over 3, which will be the exact area bounded by the spiral above the x-axis.